All right, so the first two videos just kind of generally talked about Kc, and we're still kind of generally talking about Kc and equilibrium constants. In this video, we're going to start out by talking about how, we said that Kc requires you to have a balanced equation. Well, what happens if you change the balanced equation? How does that affect Kc? So that's what this first little part's going to be about. So let's just look at an example. Okay, so we have this reaction 2NO plus O2 at equilibrium forms 2NO2. Doesn't even matter what this reaction is, and we have a Kc value. Kc is 4.67 times 10 to the 13th. This is a huge, huge Kc value. Okay, 10 to the 13th is a lot. This is basically like 4 with 13 zeros after it. So what this means is, based off what we saw in the last video, the very last thing that we talked about, if Kc is larger than 1, the reverse reaction should be dominant. Well, this is significantly larger than 1. So what this means is the reaction is predominantly going forward. So this is significantly more stable than this, and the reaction's mostly going that way. Okay? And we could write out what Kc is equal to. This doesn't really tell us anything new, but I just kind of want to get you extra practice at seeing how this works. So it'd be products over reactants raised to the coefficients. Okay, great. Some random Kc value. We're not even doing any calculations with this. What we want to know is what happens if you reversed this. We saw with Hess's law and stuff like that last semester that you can reverse reactions. So we want to know if you had this reaction instead, what would the Kc be? I am going to give this a little symbol. It's called Kc prime. This prime does not mean anything in particular. It does not mean that I have reversed this. I am reversing it, and it's a pure coincidence that this gets the prime symbol. What we want to know is, what's the Kc for this reaction? We know that when you write it this way, it's 4.67 times 10 to the negative 13th, which means it's predominantly going this way. Well, now we flipped it, so it should be predominantly going this way, so we expect a number significantly less than 1. Okay? Well, if we tried to write out the formula for this equation, which I'm now calling Kc prime, it would be products over reactants raised to the coefficients. So it's NO squared times O2, supposed to be a bracket, concentration of NO2 squared. Okay? Well, you'll note that these are not dissimilar. They're essentially flipped upside down. Okay? So this is essentially equal to 1 over the original Kc value, which means you don't actually have to go through all this legwork. You could literally just say, oh, we reversed the reaction. We need to take 1 over Kc. So it's going to be 1 over 4.67 times 10 to the 13th. And none of these things have units. It comes out to 2.14 times 10 to the negative 14th, which makes sense based off what we said. We said that the forward direction is it's primarily going towards the NO2. That's what this number tells us. And this is also telling us this. This is a very, very small number, very much smaller than 1, so it's going to go primarily that way. It tells us the same information. It's not the same number, but they are related. The important thing is, if you reverse a reaction, you do the reciprocal of the Kc value. Okay, so let's say we had another variation of this, where we just had NO2, so obviously related reactions here, forms NO and 1/2 of an O2. So in other words, we took everything from here and divided it by 2. This is a different Kc value, so I'm going to call it double prime. This double prime does not mean anything specific. It's just saying that it's not the same as the first two. Okay? I'm going to write out this form of it. So it's going to be concentration of NO times concentration of O2 raised to the 1/2, basically the square root of that thing, divided by the concentration of NO2. Well, in terms of comparing any of these, it's similar to the second one, right? And it makes sense. This reaction is similar. We just divided everything by 2. But what we see is that all the exponents got divided by 2, which is the same thing as saying it's Kc prime raised to the 1/2, which means the square root. Whichever way you like to write this, it's the same idea. Okay. We also said that Kc prime is 1 over Kc. So you can also visualize this as 1 over Kc to the 1/2. So you could start from here, take the reciprocal, and then take the square root, and you would get this number. And the answer comes out to 1.46 times 10 to the -7th. And so for this one, it's still much less than 1. It's telling you the reaction is predominantly going this way, but just not as fast because it's dependent on concentration, and we basically cut the concentration in half by we halved all the coefficients. Okay. The important thing here, I do not care about these specific numbers. The important thing is if you have a reaction, if you reverse it, you do the reciprocal. Okay. If you have everything, that's what you do to the exponent. If we had doubled everything, you would square this number. If we had tripled everything, you would cube this number. If we had, if we had some random reaction and we reversed it and cubed it, or reversed it and tripled it, you would do 1 over it and you would cube it. You would do both. So it doesn't really matter what order you do things in, but that's how you manipulate equations. Okay. All right. I want to look at an example that's still also somewhat related. And we, in the last chapter, talked about mechanisms. I want to look at a mechanism and kind of see how Kc is related to all of this stuff. Okay. So we're going to call them A and B. And they're going to be kind of similar to the last couple reactions we looked at, but not exactly the same. So N2O plus 1/2 O2 is at equilibrium with 2 NOs. And the Kc for this A reaction is equal to 1.7 times 10 to the -13th. Okay? And then the second step of this reaction is that the 2 NOs that we produced here are now going to react with another mole of O2 and form 2 NO2s. So this is Kc for the B reaction. And this value we actually did see in the last one. It's 4.7 times 10 to the positive 13th. Okay. So this is the proposed mechanism. So what we want to know is, what is the overall reaction? Okay. Well, essentially you would add up all of these reactants and all these products and cancel out anything that's the same. The stuff that cancels out is these 2 NOs. The 2 NOs form here and they get canceled out here. They're still part of these reactions, but when we add it all up, they kind of disappear, and this becomes 3/2 oxygen or 1.5 oxygens, whatever. So we have N2O plus 3/2 oxygen forms 2 NO2. And this will have a Kc value, and that's what we want to know is, what is this? Okay, so this is the overall reaction. Okay. Before we get too far here, though, which one is the slow one? Like, we have 2 steps. Which one is the slow step and which one's the fast step? We said in the last chapter that things that have like a bigger a bigger activation energy are the ones that are going to, like, how much energy it requires to get over that little hump, is going to determine what's fast and slow. But it turns out that these things, as we said earlier, are based on, in the last video, are based on reaction rates. So this stuff is affected by reaction rates too, and we can use it to get information. Honestly, if you look at this, this is 10 to the -13th. This means this reaction primarily goes backwards, which means it's probably not going to be super fast. This reaction is 10 to the 13th, which means it's going to go predominantly in the forward direction. This should be the fast reaction, and this should be the slow reaction. Okay, we don't know what this is going to look like overall, but that's okay. So I'm going to kind of just show you the answer and explain how we got there. Okay, so if we look at the Kc, like the general form of the products over reactants, for the first reaction, it's concentration of NO squared divided by N2O times concentration of O2 to the 1/2. Okay, right, products over reactants. I'm gonna put that in a parenthesis. And if we have the second one, it's gonna be NO2 squared divided by NO squared and O2. It turns out that if you multiply these, you should get, I don't know, something useful. So the only thing that should cancel out is this is NO squared and NO squared. And not by coincidence, it's the same thing we crossed out up here. Okay? So, if we add up what we've got left, we have NO2 squared, N2O on the bottom, and then we have O2 to the 1/2 times O2. So basically you would add the exponents, so it's O2 to the 3/2. Which if you look, this is the Kc for reaction C. It's basically this squared divided by this to the 3/2. Okay, so the other way you could visualize this is it's essentially Kc of A times Kc of B equals Kc of C. So in other words, if you have a mechanism, even if it's 78 steps long, if you multiply all the Kc values for each of the reactions, you should get the overall reactions Kc. So for this one, it comes out to 1.7 times 10 to the negative 13th times 4.7 times 10 to the positive 13th. Honestly, the 13ths kind of cancel out, and you get an answer of 8. No exponent. Okay. So mechanisms don't necessarily come up a whole lot when we talk about equilibrium constants, but this is how you would deal with it. I'm not saying you never see it, it just doesn't come up as common as some of the other stuff. Okay, but it is all related to the stuff we saw in the last chapter. All right, thank you.